example 1 here on implicit differentiation is taking a look at implicit differentiation. So we've been given this equation here and we're asked to find dy by dx, and we require here implicit differentiation. So we're going to go along term by term and differentiate implicitly where it's required. So my first term here, 4x cubed, well, that would simply give us 12x squared. So that's 12x squared there. For this next term here, 23 sine x cos y, this requires the product rule. Okay, so we're going to differentiate implicitly, but also use the product rule. So if we differentiate this correctly, what we get here is plus 23. So plus 23 cos x cos y. Cos x cos y. And we also get minus 23 sine x sine y. And then we need to times this by dy by dx. So dy over dx. Okay. For this 36xy squared here, again, we require the product rule. So what would this give us here? Well, that would give us plus 36y squared plus 72xy. And then again, we times this by dy by dx. And finally then, for the plus 12y here, if we differentiate that, that would be plus 12. We just need to times it by dy by dx. Okay? And clearly the 1 here would just differentiate to 0. It's just a constant. So this is all equal to 0. So here now, what we're looking for is dy by dx. So what I need to do here is collect all the dy's by dx on one side and then move everything else across to the other side. We need to rearrange for dy by dx essentially here. So what I'm going to do first, I'm going to take this minus 23 sine x sine y dy by dx onto the other side, just so that's positive, but this doesn't particularly matter too much, okay? So what I'm going to get here is 23 sine x sine y dy by dx, okay? We're also going to get a minus 72xy here, dy by dx, so minus 72xy dy by dx. We're also going to get minus 12 here. So taking all the dy's by dx's across to the other side, we get minus 12 dy by dx there. Okay? And this is going to be equal now to the remaining terms. So what have we got left over here? Well, we've got a 12x squared. So we've got 12x squared there. We've got the plus 23 cos x cos y. So plus 23 cos x cos y. And we've also got here a plus 36y squared. Okay, so plus 36y squared. Okay, so that's dy by dx, that's also dy by dx. So we've got everything we need there. So here we want to find dy by dx. So what I'm going to do first is consider this left hand side and factor out my dy by dx. So if we do that, what we get here is 23 sine x sine y minus 72xy minus 72xy, and finally minus 12 there. Okay, and that's for dy by dx. Factoring that dy by dx out. And that's clearly just still equal to the right hand side here. So this is all equal to 12x squared plus 23 cos x cos y plus 36y squared. So finally here, what I want then is just dy by dx on its own. So to do that now, we're just going to divide by this 23 sine x sine y minus 72xy minus 12. Okay, if we do that, then clearly we just get left with dy by dx, which is going to be equal now to this fraction. So in this case, if we find dy by dx here, so dy by dx, what will this be equal to? Well, it's going to be equal to this expression here divided by this expression. So if we write that in full, and let's write this in a different pen colour just so we can see clearly. So this is going to be equal to 12x squared plus 23 cos x cos y plus 36y squared. And this is all over now. 23 sine x sine y minus 72 xy minus 12 there. Okay, so that gives us everything we need there for example 1 and gives us our solution. Let's take a look then at example 2 for implicit differentiation, which is taking a look at inverse trigonometric functions. So here we're asked to find the derivative of arc cos of x. So if we write this as y equals arc cos of x, well, the first thing I'm going to do here is take cosine of the left hand side and the right hand side of this equation. So in that case we'd get cos of y, and this is equal to x. If you take cos of arc cos of x, that would just simply give you x. And here now we can differentiate this implicitly. So if we differentiate here implicitly, what we get is minus sine y, so minus sine y. Remember we times this by dy by dx, so dy by dx, and this is equal to 1. Okay? So now what we want to do is rearrange for dy by dx. So to do that, we're going to divide the left hand side and the right hand side here by minus sine y. So therefore we get dy by dx. Dy by dx is equal to minus 1 over sine y. Okay. So here now, again, like we've seen with the previous example for inverse trigonometric functions, what I'm going to do now is just rewrite this denominator here. So dy by dx, well, rewriting the denominator here ever so slightly, we can write this as minus 1 over the square root of sine squared of y. Okay, and the reason we do this is so we can use our trigonometric identities, because we know sine squared of y plus cos squared of y is equivalent to 1. So therefore, rearranging this for sine squared of y, we can say sine squared of y is equivalent to 1 minus cos squared of y. So in that case, substituting this in then, what we get here is minus 1 over the square root of 1 minus cos squared y. But we know cos y is equal to x. So in that case, we can now use x equals cos y and put this back into our equation. And what we obtain here is that dy by dx is simply equal to minus 1 over the square root of 1 minus x squared there. Okay, so minus 1 over the square root of 1 minus x squared. And that gives us the solution to example 2 there for implicit differentiation.